Well, eccolo, as they say in Italian. Here it is, or maybe Carmine, eccoci is the more precise word for here we are. So here we are with a new episode of Sustainability Forward, our podcast on all things related to sustainability. Last few episodes, we've had very interesting discussions with some of our guest speakers, and we've developed an understanding of many different aspects, starting from macro to micro, and including people issues. Today, we extend the conversation into the world of utilities with a guest speaker, James Crosby-Wrigley. And with me, as always, is my co-host, Carmine. Carmine, would you please introduce James?
Yes, thank you, Rishi, and good Italian, by the way. So I wish I could speak also more languages as you do. By the way, so we have Dr. James Crosby-Wrigley today. So James is the head of sustainability for commercial and industrial energy supply and usage at Advantage Utilities. He has a Ph.D. in Geochemistry, Geological and Earth Science, Geoscience, from the University of Cambridge. James now offers business support to a range of companies who are looking to achieve net zero and manage their energy costs through sustainable energy solution. So, James, welcome to the show.
Ciao, Carmina. How are you doing?
Good, thank you. Thank you for being with us today.
Right.
Oh, it's wonderful to be to have this platform to talk a little bit about what I do on a daily basis and provide it to your excellent audience.
No, thank you, James, for joining us. There are lots of questions on our minds. We know our audience always is interested in various aspects of the energy system, but one particular topic that we thought we could start with is the topic of distributed energy systems. We understand that's an area that's that's in focus for you. So to start off, could you help our audience understand what are distributed energy systems, and in particular, what is their role in decarbonization and sustainability?
So let's set the scene. The energy sector, the energy landscape as we understand it. When we think of generation assets or the ability to generate power, we most commonly think of what's called an embedded generator. So these are your very large wind turbine farms. These are your large solar producing facilities. These could be your pumped hydro facilities. These are generators which are called embedded generators, which generate electricity purely to feed into the grid, and then the supplier will distribute that power throughout the grid to the necessary user. My particular area of expertise or focus is what's called a distributed energy system. Now, a distributed energy system is also known as a beyond the meter solution. So when you've got an electricity meter, which is the interface of the national grid or the grid system with a particular facility, a particular building, the distributed energy generator feeds beyond the meter. So it's supplementing or circumventing the need to consume from the grid and directly feeding electricity and power into the building as a generator which the building owns or has access to provide their necessary power. So that's and a really good example of this would be, say, a rooftop solar generator. It could be a proximally located solar carport. It could be a wind turbine, which is located very close and then fed into the main electrical incoming supplies. Or if you're in a particularly unique setting when you've got the access to, say, a flowing river, you can have a hydroelectric facility, which is, again, feeding in directly for the use of power, for generating power directly for that site.
Okay, excellent. Now, these distributed systems, do they then talk to the grid as well in some way?
They do. So it really depends on the nature of the local grid. So in order to connect a distributed energy system, you of course need permission from your local grid operator. So the district network operator, the company in charge of ensuring that the grid is operating safely and reliably, to have a distributed energy generation system, you would need to apply to this DNO. Now, what the DNO is going to do is understand what the local environment is like. Have you got the sufficient power capabilities? Have you, and most importantly, what they're looking at is, do they have capacity for you to export the generation back into their network? Because that's what they really care about, is you are producing a new generation asset into their infrastructure, so you can have it installed pretty straightforwardly if you don't want to have any exported energy going back into their system. However, if you do want to have the ability to export the excess generation, then the local network operator is going to require an investigation and some analyses. This can typically take 45 to 90 days, depending on the size of the system. But yes, so the answer to your question is the local network will care about permissions for you to install these generation assets.
Okay, that's very interesting. We very often hear that distributed energy systems are a critical component of decarbonization, sustainability of the energy overall energy system. How do they specifically help with that?
Sure. So let's go with some data. So what's really important is the national grid. Let's look at the United Kingdom, for example. So every year, carbon intensity values of the energy grid are published, and although more green generators are coming online, the actual carbon intensity value of the power being applied to the grid is increasing every year. Now, you've got an example of, say, wind turbines and solar PV as from their embedded sources into the actual grid. Those are low carbon forms of energy generation. But you also have CCGT plants, the gas combustion plants. And they're very carbon intensive generators. As a result, you end up having approximately 0.2 kilograms of CO2 per kilowatt hour being consumed from the grid. So if I'm a building occupier and I'm purchasing my energy from the grid, well, I have to use 0.2 kilograms of CO2 for every kilowatt hour that I've consumed from there. Now, in comparison, a distributed energy system for solar or for wind turbines is significantly lower. So the real environmental benefit you get is that you've got a significantly lower carbon intensity value. A really easy metric we can use is understanding what the embodied carbon value of a system is. And embodied carbon is carbon that is required to be emitted during the manufacturing and installation process of a distributed energy system. When we do the calculations, the amount of time that it takes for a distributed energy system to offset the amount of carbon that would have been emitted from the grid is 2 to 3 years. So what you end up having is a approximately net zero source of energy from your distributed energy system within 2 to 3 years. So that's why it's so important, is because it is a point of origin, low carbon, renewable energy source, which is able to offset what is quite a carbon intensive national grid, at least in the United Kingdom.
Okay, that's great. James gives us a good understanding. Thank you.
Thank you, James. But in your example, so as a follow-up question, so you're referring in a case where the main grid is supplied mostly by conventional energy. So it could be gas, coal, and then the distributed energy system is, for example, renewable energy, so solar and wind. So that's probably at the base of your assumptions.
Well, so the national grid, of course, is a mix. it's a complete mix. But what I'm doing is taking the published values of the mixed form of energy generation that is published very transparently on government websites, and using that value because what happens is electrons are electrons. They don't really care where they come from. And what ends up happening in the national grid is you end up having a soup. So you have to use the average soup value and compare that to the known point of origin generation asset.
Got it. Thank you. So you can talk a little bit more about this ecosystem of distributed energy systems and what it looks like, and some example of who are the main players and what their roles, at least looking at UK, that is your main market.
Sure, well, happily. So it all starts with the actual site that you would want to install a distributed energy system, the building, the facility. And there are three main players in the actual site itself. You've got companies that are owner-occupiers, so they own the building, they occupy the building, they've got all the rights to the building, and that's a relatively straightforward conversation. They're the people that are able to make their own decisions about, okay, this is our building, this is our facility, this is our site, and we would like to explore further additional distributed energy systems. Another area of this in the site constraints is the landlords that can own the site. So quite often you'll have landlord-tenant relationships, and under distributed and under permitted development and license to alter property ownership laws, the landlord's actually the one that has the ultimate say on the ability to install these distributed energy systems. And then the third main player in terms of the site and the building constraint, of course, is public sector facilities. So these are, government owned and operated buildings. It could be healthcare, it could be council buildings, it could be schools, it could be educational facilities, and these now end up falling into local decision makers within this particular public sector. But they have a slightly different decision-making process than a landlord would. That is, again, also a slightly different decision-making process that an owner-occupier of a building would. So in terms of the main ecosystem, we can break it down firstly into the actual buildings themselves and the typical occupants / owners of these buildings. Then the other three main areas to talk about in terms of the ecosystem is the actual hardware providers, the actual engineering, procurement, and construction, the installation side of things, and last but not least is the funding mechanisms. So the ecosystem is half of the conversation is the actual owners and occupiers of the buildings. And then we want to get once it's understood about these the site and who the owner, the occupier is, then we want to get into a little bit more of a detailed conversation. Then we go into funding mechanisms. Are the particular owner, occupiers, stakeholders of this site, how would they be looking to undertake the installation? Are they looking to actually fund the installation themselves with their own capital expenditure? Alternatively, are they looking at potentially undertaking some asset finance? Or last but not least, are they looking at maybe a power purchase agreement or some kind of cooperative? And that's when we need to understand the funding landscape of the stakeholders of the ecosystem. So commonly, if you want to capex it, then that's all to do with the owner occupier having the budget to undertake the capital expenditure. Now, if they're looking at undertaking more of a funded route, then you would look at the banking institutions. You would understand what the different specialist green finance terms are. You would understand, are there the ability to obtain grants for these installations? And that's when you could then use these grants, use these specialist financing terms. Instead of undertaking a top-heavy capital expenditure installation, you could instead move on to the asset finance. You could look at, which is, of course, 3 to 7 year terms are most common. And last but not least is, of course, power purchase agreements. A power purchase agreement is you're probably quite familiar with this in the embedded generation system. It's where they install a wind turbine, they'll install a rooftop solar PV system, a carport system, and they'll say, okay, we will undertake this full installation and you will purchase all the power or a proportion of the power that's generated by this system, a certain pence per kilowatt hour, pounds per megawatt hour, euro per megawatt hour, cents per kilowatt hour. These power purchase agreements are also transferable not only from these large scale embedded generations, but also now into the smaller scale generation systems. And then that's the high level stuff. We've got the ecosystem of the building, the site owners. Then we've understood how would they be looking to undertake the expenditure or the funding for it. And then we really need to get into the details of what the main equipment providers are. So to say, for example, in solar, some building and operators, they have particularly tight constraints due to their buildings insurance providers. So then we actually need to understand what those insurance constraints are and work with a particular type of, say, panel, which has got a particular set of technology associated with it. A really, really common example is for some insurance providers to be very, very concerned about the rooftop fire health and safety risk from solar panels. So as a result, you've actually got varying levels of safety associated with different panels. And of course, the more safety features with these panels, the more expensive. So if you are a very safety conscious insurance provider, you're a very safety conscious building owner or occupier, then we need to make sure we're specifying the right equipment. And then last but not least is, once we've understood the building site occupier, we've understood what kind of funding mechanism we're looking at, then we've also understood what type of equipment we're looking at. We want to look at who actually is going to undertake the installation and the reputation of the company, because there's not actually that much legislation, at least in the United Kingdom, regarding installation companies. You've got micro generation scheme, MCS. You've got certain industry standard bodies that you need to conform to, but what's happened in the past is you've had certain installation firms that were around for 3 to 4 years and given a 5 to 10 year warranty on their workmanship, but what they've basically done is gone bust. And now this workmanship is all completely defunct because there's no installation firm to take it up with. So you want to make sure that you're picking the right installation firm that's going to be around for long enough to be able to claim their workmanship, but then also is reputable enough to install a really high quality, really safe system for wind turbines, for rooftop PV. So to answer the question, in the ecosystem, we can break it down into 4 main areas: the site occupiers and the nature of the site occupiers, the funding mechanism that those site occupiers are looking at, the constraints that those sites may have on the equipment they need to use, and then last but not least, obtaining the correct and most reputable installation firm to complete the project for these building owners.
That's good. That certainly looks like a multi-stakeholder play when you get into these projects. One thing I was curious about, James, is you gave us a bit of a data point earlier on about the carbon intensity of the grid. Is there any historical evidence that suggests that distributed energy systems have been able to make a dent in this carbon intensity? How has the progress been so far in terms of lowering carbon intensity of supply?
A really good question. It's going to be a disappointing answer. The easy answer is it's incredibly hard to calculate. It's really hard to calculate. And secondly, the calculations that we are able to make, what ends up happening with distributed energy systems is they're actually really quite small in volume for the amount of power that they're providing to the grid. the way that PV systems are and embedded wind systems are sized is they're predominantly installed to offset or to supplement a certain proportion, say typically 25 to 30% of a site's total load. So what ends up happening is when the PV system or the wind turbine system is sized to that, you end up having a slight excess generation, this export volume, or otherwise known as a spill volume. And that spill volume is then being sent back into the grid. Now, what's really good about distributed energy systems is they are dominated by low carbon technologies. They are dominated by solar and they are dominated by wind. The main problem we have is the actual amount of energy that is being produced in excess that is not consumed by these sites and being sent back to the grid is a fraction of its total generation. It's typically 15% to 30% of the total generation. Now, when you've got such a small proportion being sent back to the grid, we then also have to look at the size of these generation assets. Now, I don't know the exact statistics, but the distributed energy capacity, total installed capacity, is significantly smaller than the embedded installed capacity. So what ends up happening is you've got this quite small amount of excess or this spill volume from a relatively small, from a smaller generation capacity being sent back to the grid. Therefore, although we will be able to reduce the energy intensity and capacity of the national grid, it will reduce it, but the actual significance on this is not as great as it could be.
I see. Interesting. Oh, good. That gives us an overview of where we are with the distributed versus embedded system.
So, James, now you have some very good experience here in this field. What do you think are the main challenges that are being posed by the distributed systems on the conventional systems, and how do you think we resolve them?
So it's a question that actually distributed energy stakeholders and embedded generation stakeholders would be on the same side of the table on. It's a question of the network. There's a major problem with the network. We, as distributed energy stakeholders, have the same opinion as embedded generation stakeholders. Want to install as much as you can, which is done correctly, and we want to make sure that the process is as straightforward and as easy as possible. Now, a major area of red tape and barrier to entry is the national grid. It is that national grid, because not an absolutely essential, but it's still an important factor for the economics of a distributed energy system is the ability to have an exported volume back to the grid. Now, what's happened is the grid is, some would say fried, some would say at capacity, some would say a little bit in need of dramatic upgrade. I would say it is a major challenge because we all want to export whatever energy that is not being used on site back to the grid. Just like embedded generators want to install as much capacity as they can, but they are limited by the amount of capacity available on the grid. So what ends up happening is during this assessment phase, we end up having to undertake analyses of the actual capacity available for this particular distributed energy generation system in the particular area. What that means is if I want to export, say, 100 megawatts or 100,000 kilowatts, is the grid actually able to do that? And if the answer is yes, then great, happy days. Let's get full export, full G99, which is G99 is the export legislation. Great, let's do that. Quite often, what will happen, but not all the time, is you'll either get a limitation on the amount that you're allowed to export, or you'll get a absolute zero export offer. You can generate, but you can't export anything. And that is then would fall akin to what's called G100 legislation. Now, there's there's two key ways around this. The first one is, okay, let's just decrease the size of the system. It's going to cost you less to install it, and you're also going to have less amount being spilled or exported back into the grid. Yes, we lose out on the particular export income, but that way we're only paying to install a system, a generation asset that we need to install. The next way around this, and this is the big question, is the actual cost-benefit analyses of utilizing battery energy storage systems. So let's look at the residential market, for example. Batteries are quite ubiquitous because of operational profiles. Most people are home in the evening, not around in the day, so they store the excess generation into their battery and discharge it at nighttime. Now, what could happen with battery storage systems for the commercial is quite simple. It's the same thing. It's for this excess energy that's being generated, instead of exporting it back to the grid, what if we fill up a battery and then discharge that at nighttime for solar or for daytime for wind, for example? The challenge that we have at the moment is the actual cost of the battery. Batteries are incredibly expensive. They are a very expensive system relative to the cost of the installation of, say, solar and PV, relative to PV and wind turbines. They are very expensive. And secondly, their payback is significantly longer than that of PV and that of wind. So that is a very obvious route to mitigating the limitation on exporting is, what if we use batteries? The less obvious and more challenging thing is, what if we use batteries but also still make it economically viable? That's a much harder challenge. Now, in order to get there, we need two things, in my opinion. One of them is we need battery prices to come down, which of course is dependent on technology, depending on the evolution of the manufacturing process, which is outside of my control, obviously. But we need the price of the battery to come down. And then secondly, it would be great if we could have a more sophisticated and affordable arbitrage model. So say for grid services with embedded battery storage systems, they'll store up their excess generation during potential negative pricing moments that we've seen in Germany and sometimes in the United Kingdom, and they will store that very cheap energy and then sell it at a later date or a later time in the day and arbitrage that. Now, the problem is that in these distributed energy markets, in the site specifics, for that to make financial sense, you need a whopping great at least 1 megawatt battery. Now, in embedded generation markets, a 1 megawatt battery is run of the mill. That's nothing really, that. But to a distributed energy player, that's a significant investment, a real significant investment that's got a lot of misnomers, misunderstanding. So we need to make that a little bit more transparent. And if we can do that, then we can get more affordable batteries, which are able to undertake more sophisticated activities. Then that's a way around the grid problem we're currently facing.
Interesting. In fact, this has parallels to some of the things that we are used to working on, which is when, for example, when you build a smaller sustainable fuel production unit to a major refinery, which you can think of as an embedded system, you get into very similar contractual or technical or operational issues, and it's not necessarily easy to resolve them because you are essentially being part of such a big existing system. And now that James, we've established a basis for what the distributed energy system looks like and what are the challenges. Maybe one of the last questions that we have for you is, how do you see this space evolving going forward? And do you see room for new players, new commercial models, or even new technologies to emerge in this space, which will alleviate some of these challenges or help the expansion of this distributed system overall?
So I actually was really fortunate, and I had the opportunity to write an article commenting on how the market has evolved, with particular comments on government support. So in breakdown market evolution into all these different, let's first talk about government support. In the past, we saw quite a lot of government support as low carbon technologies, especially distributed energy low carbon technologies, came into the market. There was the feed-in tariff, so that was huge. If you're on the feed-in tariff today, you can be making upwards of 15 pence per kilowatt hour, or 15 pounds per megawatt hour, which is great income just for generating, right? That's one form of support. The other thing is there was also quite a lot of government tax incentives. There was a lot of green financing solutions. That is how the market was, say, as little as 5 years ago now. That's when the feed-in tariff closed in 2019, I believe. So as little as 5 years ago, we had a lot of government support. And the whole point that the government was looking at was they were using the carrot. So it's called the carrot and the stick hypotheses, is what I called it. It's the carrot, transitioning from the carrot to the stick. We 5 years ago had a lot of carrots being dangled in front of us as site owners, occupiers, to install these PV systems and install these install these distributed wind generation systems. What's ended up happening is the feed-in tariff's gone. It's been replaced with the smart export guarantee, which is an absolute fraction of what the feed-in tariff was. The tax super deduction, which was excellent, it was 120% deduction off your year-end corporation tax for installing any of these suitable technologies. That's gone. That's been replaced with full capital first year allowance. And then the grants that were predominantly from the European Union, actually, to the United Kingdom. Well, of course, they're gone, because that's what happens when you Brexit, is you lose a lot of access to this European funding. And so not only have we had the removal of the carrot, so to speak, but also energy prices have shot up, absolutely shot up. We know that, say, the levelized cost of electricity of a typical PV system is between 4 pence per kilowatt hour, or approximately 5 cents per kilowatt hour, to 7 pence per kilowatt hour, 7 cents per kilowatt hour. So that's significantly lower, especially in 2022, when we had the Russian-Ukrainian crisis, which caused wholesale markets to completely skyrocket, peak at something like, I think it was 80 cents per kilowatt hour, or 800 pounds per megawatt hour. That was crazy expensive. So they said, okay, well, we want everyone to. The government's approach, in my opinion, was we've given a lot of carrots out. Now we've got no carrots left. But actually, energy prices are really high. We are issuing the requirements for carbon taxes. Say you emit over a certain volume, then you will be taxed, and you have to enter the compulsory carbon market. We also are putting a lot of pressure on you from your important stakeholders, are questioning you about your environmental credentials. These are all sticks, in my opinion. And what's now happened is the distributed energy market has transitioned from, look at all these carrots, look at all these grants, look at all these incentives to install PV, it's to now being in a position of, well, wow, energy prices are so expensive. I need to reduce my carbon output. I'm also being put on pressure by my stakeholders to reduce my carbon output. These are all sticks. And as a result, now people are having to be more reactive and more preventative of bad things happening, as opposed to looking at the good things that can happen. So that's one way that the market has evolved. Where's it going forward? Well, let's be honest, there's not really going to be any more government support, because now solar PV is such and wind is so supported by the economics that it kind of stacks up in its own business case. What's really happening and what's really great is what's called permitted development laws. So permitted development laws mean that you can install distributed energy systems without having to do a full planning application. It's called a prior application notice. And that's really great. And what's happened is that has been expanded. And especially in the last 12 months, firstly, we've had the removal for many systems of removal of the 1 megawatt peak limit before you need to do a full planning application. Now it's 5 megawatts, which is great. That's one example of how these red tapes are being removed. And then in Scotland, huge piece of legislation passed only a few months ago, which is it was a rooftop PV installation was limited to just 50 kilowatt peak. And if you wanted to go above 50 kilowatt peak, you needed a full planning application. Well, now that's been removed as well. So that's one area of how the market's evolved, is to remove the red tape. Now, the other area, that's a legislation piece. Like that's great. The other problem is that's what I would call the good market evolution. Another example of a good market evolution is improving tech. This technology is becoming more efficient over time, which is great. But to allude to a previous conversation, is where the grid is only getting busier. And I see that becoming more of a challenge going forward for reasons as previously discussed. That puts a lot more pressure on these district network operators, on these independent district network operators, to try and enhance their local grid, to make the installations more viable for the spill and the export.
Absolutely.
Thank you, James. I think that's very good, let's say, insight, overview of what a distributed energy system is. Today we learned a lot, I think, Wrishi. So just to summarize, we learned what is the difference, what this ecosystem is, what are the main players from the occupiers to the funding mechanism. This is quite interesting. The constraints that are happening there, or we talk about the insurance company, we talk about the installation and what it takes to have the reputable installation companies to use. We learn about the challenges, what could be the bottlenecks there, and the importance of the grid as the main one, and also a good understanding on how the market is evolving. And a lot of content. It's been a very rich episode. I would like to thank you, James, for being with us.
Well, thank you very much for having me on this podcast, Sustainable Gang. And well, let's keep fighting the good fight.
Absolutely. And as always, for our audience, we are under the banner Sustainability Forward on LinkedIn and all major podcast platforms. Thank you again for joining us today. Take care.
Thank you.